Hi guys, sorry I'm not there today. We are focusing on Unit 7, okay? And Unit 7 was one that we did pretty good. There was areas we struggled with, especially that like molar solubility stuff. So I want to walk through this first page with you. Make sure you grab one of these Unit 7 in class reviews. When I get back, I'll be checking off your notes for today and next time as well. Okay, so first thing, equilibrium. Just like recognizing the criteria for equilibrium. Remember that it's only with reversible reactions when we have reactants that turn into products, but then products that turn back into reactants when it's reversible like that, then we will reach equilibrium. In order for equilibrium to be, or the requirements of equilibrium to be reached, we need to have the rate of the forward reaction as to equal the rate of the reverse reaction. So if I have a rate versus time graph, okay, we'll probably see, likely, that we start with a really high forward rate and a low reverse rate, and the reverse rate increases and the forward rate decreases until they equal each other. This is the point that we got to equilibrium, where this represents the rate of the forward and this one represents the rate of the reverse reaction. So when the rate of the forward equals the rate of the reverse, something else occurs, and that's when the amounts or the concentrations of the reactants and the products, they stop changing. They become constant. Not equal, but constant. So we'll say stop changing. So when the concentration of the reactants and the products stop changing, then we have reached equilibrium. So there's a couple different ways that those graphs can look, but usually we see something like this, where here's concentration versus time. Reactants usually start off high and then decrease. Products usually start off low and increase. They can be equal, but it's not common that they are. It's when they level off here that we get to equilibrium. I've also seen with this concentration versus time graph something like this before. Okay. This is not equilibrium where they equal each other. It's when they level off. It's when they stop changing. So right about there is when we've reached equilibrium. Okay. Now, Le Chatelier's principle, this is when we add a stress and then the equilibrium will shift as a result of that stress. So we get this shift in equilibrium. Okay? Good. So when we add a stress and then we see a shift in equilibrium because of that. A couple things I want to remind you of. So we have reactants. Let's say we have one reactant, it's going to be a solid. We have another reactant that's a gas. And then let's say this turns into, back and forth, maybe a product that's a gas, and let's say we get like 2 of them like that. Okay, so the other thing is endothermic versus exothermic, right? If delta H is larger than 0, this would be endothermic, and we would add heat on the reactant side. But if delta H is less than 0 or negative, then it's exothermic, and then we'd add heat on the product side. We could say maybe for this fictitious one here that it was exothermic, and so I could put heat over there. Now, there's a bunch of different stresses that we could put on this reaction. We could add or take away this reactant or that product. The solid, it wouldn't matter so much, but gases or aqueous, we could add or take away. We could increase or decrease the temperature. We could also increase or decrease the pressure. So for example, let's say that we are trying to maximize the amount of product that we're making. Like, let's say we want the reaction to respond by increasing more of this product. Well, in producing more product will only occur if we are favoring the forward reaction, right? When reactants turn into products. So that would mean that our reactants are going to go down and our products are going to go up. A stress that is opposite of that will make this occur. For example, if we increase the amount of this reactant, then the reaction would respond by trying to decrease it, which would make us favor the forward reaction. So there's one potential stress. We could, these are the stress, okay? So we could add some of this R. That's a gas. We could do that. Now the reactant, that's a solid, this doesn't work. You can't change the concentrations by adding or taking away a solid. So because this guy is a solid, solids and liquids, that won't work, okay? The other thing that we could do is we could decrease the temperature. Okay. By decreasing the temperature, the reaction responds by trying to increase the temperature, which would cause us to favor a forward reaction and produce more of that thing that we're wanting. The other interesting thing is pressure. So pressure and equilibrium. So for this example that I have here, I have one solid, one gas turning into two gas particles. So whenever we're dealing with pressure, I want you to count up those gas particles. On the reactant side, we had one gas particle. And then on the product side, we have two gas particles. Okay? And if we're favoring, or we want it to favor the forward reaction, do you see how that's going to be one gas particle turning into two gas particles? That would be an increase in the pressure. But if we want the reaction to respond by increasing the pressure, then another stress we could do is decrease the pressure. And so if we decrease the pressure, the reaction will respond by trying to increase the pressure more, trying to make one gas particle turn into two gas particles. So don't forget that equilibrium is also related to the pressure. Okay. This idea of something dissolving in water and solving for KSP or molar solubility, this is really where we seem to struggle the most. Let's do an example one. First off, this little SP stands for solubility product. And you don't need to worry terribly about that. You just need to know that it means it's dissolving in water. So if we're trying to figure out the solubility product of something, we have to take that something and say, well, what's that equation looking like when it dissolves in water? So here's a common one. What about, let's do a polyatomic ion. Magnesium nitrate. Okay, so we're dealing with magnesium nitrate as a solid. But then if we dissolve this in water, the magnesium will break apart from the nitrate. And we know because of its location on the periodic table, magnesium is in group 2, so when it forms an ion, it's a 2+. And nitrate, we have those polyatomic ions memorized, so NO3, and it's a -1. Now, do you see how there's 2 of those nitrates, though? So we get a coefficient of 2 right there. Now, these are dissolved in water, so these ions are now aqueous. Dissolved in water. Great. I could write a K expression for this. That K expression, SP. Remember how all of these K expressions were products over reactants, but we don't include solids or liquids. So yeah, this aqueous, absolutely, but the solid, no. So we would have the concentration of magnesium 2+ multiplied by the concentration of nitrate NO3 -1. But because this is a coefficient of 2, we raise that guy to the second. So there's my reactants. I divide by my products, but my product is products over reactants. So here's my products. I divide, and I would put it over my reactants, but my reactant is a solid, and we don't include solids or liquids. So there's my K expression for this. Lovely. Now we have something important with these items that are being dissolved in water, and it's something called molar solubility. And they simplify molar solubility just to be S. There's molar solubility. But what's cool is if an ion has a coefficient of a 1 in front of it, you can replace the concentration of that guy with just S, like it has 1 molar solubility there. Where if the coefficient is 2, then you could replace the concentration of this guy with 2S. And so going back to this over here, instead of saying the concentration of magnesium 2+, I could just put S. And then instead of saying the concentration of nitrate, I could put 2S. But then don't forget that this is squared. And because this square is outside of the parentheses, it applies to both the 2 and the S. So this would turn into S multiplied by 4S squared, which becomes 4S cubed. Okay? Now there's a lot you can do with this. If they give you the KSP, so KSP is equal to 4S cubed. If they provide you with this number, then you can figure out the concentration of the magnesium or the concentration of the nitrate just by solving for S. So I could do KSP divided by 4. This would equal S cubed, so then if you do the cubed root, that would equal S. And then whatever that answer is, just don't forget, that is the concentration of the magnesium. And then if you double that answer, that is the concentration of the nitrate. Okay. Here's the other thing I've seen them do. Instead of giving you the KSP, sometimes they give you the concentration of either the magnesium or the nitrate. Let's go with the trickier one. Let's say they give you the concentration of nitrate. You have to recognize that the concentration of nitrate is going to be 2S because of that coefficient. And then if you take that concentration of nitrate and you divide it by 2, then that will equal S. And now that you know what S is, you can plug it in to your KSP equals 4S cubed. You can plug in your answer, and then you'll be able to solve for the KSP value. So that's the molar solubility stuff. Okay. The answer key will be at the front of the room, but my expectation is for you guys to make your way through this. I'm going to be getting a note from the sub. I know you guys are going to do awesome, but I need you working the whole time, working hard on this. If you finish early before the bell rings, please come show the sub that you got this done, and I'll have them like check off your name on a roster that I'll leave. If you don't finish it early, that's okay. Then I just need to hear back from the sub that you were working the whole time. Okay. Do not turn these in though, because I want you to keep them and use them to study for the AP Chem test. All right, guys, I'm gonna be with the Unified Studies trip camping, so I have no clue what my service is gonna be like. If you have any questions, email me, and hopefully I can get back to you on it. Okay, work hard. You guys got this.